Okay, here's a quick run through the practice exam. Log of 4 times root 5, the log of a product is equal to the sum of the log. So we can break that up into the log of the first number, the first factor, plus the log of the second one. And we'll write the root of 5 as 5 to the 1/2. 1/2 power is the square root. And then the third rule of logarithms says we can move the 1/2 out front. So this is log 4 plus 1/2 log 5. That's as far as we can go with that one. To contract these, the first thing we'll do is we'll use the power rule to move this inside. This 2 out front here. I'm just taking this inside. Multipliers can be brought in as powers into the argument of the log function. And now I can use the second rule for logs. The log of x minus log of y is the log of x over y. So this is log base 5 of 4 over 3 squared, which is 9. And so I've completely collapsed that guy as much as possible. Log base 4 of 5 and 4/9 can't be contracted any further. This one, the 2 once again can come in, so we have the natural log of 5 squared. And then we're trying to figure out how to write 2 as the natural log of something. So over here on the side, we can think to ourselves, 2 is equal to the natural log of what? Put that in exponential form, start with the base e, cross the equal sign 2. It's e squared. If you think about it, makes sense. The natural log of e squared represents the power to which I have to raise e to get e squared. That's obviously 2. So I've turned 2 into the natural log of e squared. Now I can use the first rule, just as I did above, and turn this into the natural log of, I guess I did on the very first problem, and in reverse. It's now I'm contracting instead of expanding, of 25 e squared. Log of a product is equal to the sum of the logs, so I can take the sum of the logs and turn it backwards into the log of a product. So there's your answer for A. There's your answer for B. Moving on to 3. So we're looking to write everything in terms of, we've got 3s, we've got 5s, and then we've got powers of 4. Any power of 4 will help. So 6 we can write as, all right, have a good night. This is log base 4 of 6 is the log base 4 of 6 over 10, right, as a fraction. That's the log base 4 3/5. So now we're in business because we can write that as the log 4 of 3 minus the log 4 of 5, using the second rule for logarithms. Log 4 of 3 is just x, and the log 4 of 5 is just y from up here. So that's x minus y. This one, if you write it as a product, it's 3 times 4. We know what to do with 3 because we have that right here, and we know what to do with 4 because it's base 4 logarithm. The powers of 4 are easy. So this thing is the same as the log base 4 of 3. That's the log base 4 of 4. Log base 4 of 3 is just x. Again, I'm working off these definitions up here. So that's x. So this is x. And the log base 4 of 4 is the power to which I have to raise 4 to get 4. So it's asking this question right here. What is that power? That's obviously 1. 300, if you break that down into factors, is 3 times 25 times 4, right? 25 times 4 is 100. There's 3 of them. We know all about 3s and 4s, and 5 is just a power of 2. So we could replace this. I mean, the power 25 is just the power of 5, I should say. That's 5 squared. So now I can break it up into a sum. A log, this should be a base 4 log. log base 4, 3 plus log base 4, 5 squared plus log base 4, 4. And this guy can come out front, get rid of it here, and put it here. It's 2 log 4 of 5. So this is just log 4 of 3 is x. Log 4 of 5 is y. This is 2y, sorry. 2y, and then log 4 of 4 is just 1. X plus 2y plus 1. So there's your answer to the first one is x minus y. This one's x plus 1. And this one is x plus 2y plus 1. All right, moving on to 4. True or false? Log 6 over log, so this thing right here is actually equal to, this is the same thing as the log of 6 over 3. So if I divide and then take the log, that's the same as log 6 minus log 3. This one here is not the same thing. This is take the log and then divide. The one on the right is take this divide. This one here is divide, then take the log. This one is take the log and then divide. Order of operations is different. They're not the same. This one's false. This one is true because you raise e to some power to get 1/5. That number is going to have to be less than 0, right? E to the 0 is 1. And in fact, e to the minus 1 is 1 over e, which is approximately 1 over 2.72. So we're not even to a fifth yet. We have to go lower than -1. We have to keep going this way. So it's certainly the power to which I raise e to get 1/5 is going to be less than 0. Anytime you get a number between 0 and 1 and a base that's bigger than 1, that's going to be the case. Here, the inverse of this function is not the logarithm. The inverse of this function is the square root. This is the familiar squaring function that you've known about since middle school. This logarithm here undoes the much less familiar function, which is 2 to the x. X squared says you give me a number, I'll square it. The one function you learned about recently, the exponential function is you give me a number and I'll raise 2 to that number. Very different. Raising 2 to a number is undone by the base 2 logarithm. Squaring x is just undone by the square root. So that's false. The log base 7 of 7 to the b is in fact b. That's because the power to which I have to raise 7, they're asking the question, to what power do I have to raise 7 to get 7 to the b? And that's obviously b. So this one's true. And if b, the base is greater than 0, then any negative power is greater than 0. Just like take 2 to the minus 100. That's 1 over 2 to the 100, right? That's a positive number. Oops. Yeah, that's right. 1 over, it's not very clear. 1 over 2 to the 100. It's a very, very, very small number, but it's still positive. It's still greater than 0. So if the base is positive, then the output of the exponential function will be positive regardless. So this thing is true. That's always true. For a positive basis, the output from e to the x is always positive. Solving this guy, you want to collapse. And then either collapse both sides or collapse one side and then whip the inverse on it. This one will collapse both sides because it's easy to do that. This is log 2 of the product, x plus 1 times x minus 4. Log base 2, 14. And since log is a one-to-one function, if the outputs are the same, the inputs must be the same. So that means this is the case. And to solve this thing, you'd have to solve. I'm not going to cover that right now because I don't want anyone to waste time worrying about it. This is a quadratic of the kind that we have not covered this year because we're behind. So I won't give you a quadratic. I'll give you some simpler algebraic expression to solve here. So I'm not going to spend the time. You'd have to multiply it out, run the 14 over factored, and use the zero product property. Most of which you've all forgotten, and I don't want to burden you with it on the night before the test because you won't need it. So just once you write the log of both sides, then you can break out the logarithms and just equate the arguments and do the algebra required to solve that equation. This one we can finish. The natural log of x minus the natural log of 2 equals 3. Collapse the left-hand side, and you get x over 2. Log of the quotient is the difference of logs. So working back from the difference of logs, we take the log of the quotient of the two arguments equals 3. And then we can just whip this into exponential form. Start with the base. There's an understood e here. So I can take that e, cross the equal sign, come back to the argument, and look, I've destroyed the logarithm. And now I can liberate this x here just by multiplying everything through by 2. I get 2e cubed equals x. There's your solution for that one. This one is solvable. This one here, for now, I just want you to be able to set up the equation. There's the equation. And tomorrow you'll get one like it, but you'll be able to solve it because it won't be a quadratic. Here, this is back to our table of logarithms. So the number is the square root of, we'll use the 1/2 power, 5.12 times 10 to the 6, I believe it is, all raised to the 1/2 power. 1, 2, 3, 4, 5, 6. Yeah. So 5.12 times 10 to the 6 to the 1/2. We go over to the log scale, where life is a lot easier. The log of x, bring out the 1/2 times the log of 5.12 times 10 to the 6. We look up 5.12 in our log table and put a 6 in front of it, because the log of a product is the sum of the logs. And so it's the log of 5.12 plus the base 10 log of 10 to the 6. The base 10 log of 10 to the 6 is just 6. So we go to the base 10 table and we look up for 5.12 and we find 5.12 goes to there. It's 7093. 7093. So, lost it. 7093. What happened? All right. 7093, I think it was, I hope. So 1/2 times put a 6 because it's plus 6. 0.7093. And divide by 2. 2 goes into 6 3 times. 2 goes into 7 3 times. Carry the 1. 2 goes into 10 5 times. 2 goes into 9 4 times. Carry the 1. 2 goes into 13 6 times. Carry the 1. You get 10 and then it's 5. So we'll round it up to, all that is 7. 3547. So now we can find x. That's the log. This is the log of the answer. We went over to the log scale because on the log scale, taking the square root is as easy as dividing by 2. But now we have the log of the answer. So the answer is 10 to that number. We can raise 10 to any number between 0 and 1 with our log table. 3 significant figures. So we'll break this up into a whole number between 0 and 1. We just have to look up 3 to the 0.3547. Our log table, 3547. 3547, closest one. 3547 would be 2.26, right? 2.26, only off by 6 10,000ths. So that's 2.26. Go back to the first exam 2 practice. And this is equal to 10 to the 3rd times 2.26. This guy right here, the one we just looked up. And we look up 10 to any power between 0 and 1. 10 to the 0.3547 turns out to be roughly 2.26. Then we move the decimal place 3 over, we get 2260. 2,260 is the square root of 5,120,000 to three significant figures. And if we square it, we should get something pretty close to that. Let's square it. Square 2260 squared is 5107, which rounds to 5 million. And three significant figures is 5,110,000. So it's off by 512. Yeah, it's off by a little bit. It's off by 1 in the third decimal place. Pretty close. All right. Moving on to the second half of the test. This is the part where you can use the calculator. You have to use the calculator to get the final piece. Remember that the final answer on the calculator is worth only 1.5 points. 8.5 of the points are based on the actual algebra. The algebra is much more important. But don't get bogged down in the calculator use. If you start struggling with the calculator, just give it up. You're only losing 1.5 points on 3 problems. So still get a solid A. On the other hand, don't just give me the calculator answer, because then I can only give you 1.5 points. So I'm looking for the algebra. The algebra, you have to show your work. So I have to know where this came from. No calculator guessing check. I want to actually see the algebra. 3/2 equals 1 plus x to the 4th. We have a variable in the base. We said we use reciprocal power. So I raised both sides to the 1/4 power, taking the 1/4 root to undo the 4th power. And so I get 1 plus x is equal to 3/2 to the 1/4. And I have to just subtract 1 to solve for x. X equals 3/2 to the 1/4 minus 1. And to make it a little easier on the calculator, I think I'll use decimal here. This is 1.5 to the 0.25. 1 to the second one, and then we'll go to the calculator. Second one is now the variable, here the variable is in the base, now the variable is in the power. And the variables in the power, we first try to write both sides as a power of the same base. But 6 and 30 are not amenable to being characterized in the same base. So we take the base 10 log of both sides. We take logs, base 10 just because that's what's on our calculator. Take the base 6 log, would be a little easier, but we don't have that on most calculators. So we stick to the common log. The log of 6 to the x equals the log of 30, just taking the logarithm, base 10 logarithm of both sides. The log allows us to move this x out front. The third rule of logarithms allows us to do that. And now I just have number times x equals number. In order to solve, I just divide both sides by the log of 6. So this thing becomes x equals the log of 30 the log of 6. All right, let's do some calculating here. So there's your 8.5 and 8.5. There's your 17. No, that's some sort of that's. Those are your A and B up to the calculator piece. So that's 1.5. I guess 3 points for 2 parts. You take 1.5, raise it to the 0.25, and then subtract 1. You get 0.0466. 1.2. 1.5 raised to the 2 minus 1. It's 1066 or 0.107 if I round to 3. So this is equal to 3 decimal places. All right, log 30 over log 6 is 30. Take the log, divided by 6. Take the log, check your order of operations. Calculator got it right. You get 1.89. This guy is. And before you move on, you should do a quick reasonableness check to make sure that McDonald's isn't charging you $400 for a Big Mac. this one certainly makes sense because 6 to the 1 is 6, and 6 squared is 36. So if we're solving 6 to the x equals 30, that x ought to be somewhere between 1 and 2, and it should be closer to 2 than 1, which is a pretty apt description of 1.89. Don't know that there's any quick way to check 1.0, 10.7%. 10.7, turning $2 into $3, that's a 50% increase in 4 years. You need a pretty hefty interest rate. 10.7% sounds like it might do the trick. That's about the best I can do on that one. That one's a little less intuitive. Circle that before I move on. I really should circle the algebra too. I mean, this is really what you need. That's the big part of it. And this is the big part of here. I need this calculator of the expression. Don't do a bunch of intermediate calculations. Give me an x on one side and its calculator expression on the other side, and do your calculation in one swell swoop. All right, consider an estimate that returns 5% annually. If you invest 1,000 today, how much is it worth in 5 years? This one's just a direct plug-in. It's basically meant to set up the second part. So hopefully this will be trivial for everyone. We'll do it in green to represent the money. So A of 5, the amount of money I have in 5 years is my initial amount of money, which is 1,000 times 1 plus R, 1 plus 0.05 to the 5th. So you just have to crank that out. We'll do that in a second. How long would it take to triple your money? Now we're turning that $1,000 into $3,000. So we're saying, how many times do I have to hit $1,000 with the 1.05 stick before I turn it into $3,000? So we're solving for t here. We don't know what the time is. We know it's going to be certainly more than 5 years, because when we plug this in, we're going to find out that in 5 years it's on the order of $1,200. Let's plug it in now so you can see that what kind of number we're aiming for here. Before you start looking, it helps to get a sense for what you're looking for. So if you make some gruesome error, you can catch it. 1,000 times 1.05 to the 5th is 1276.28. So this is 1226.78. So in 5 years, we turned $1,000 into between $1,200 and $1,300. So we're nothing like tripling it. Right? We haven't even doubled it yet. I'm even close to doubling it yet. 1276. That's a 7. This is a 7. 1276.28. I interpose the 7 into 1276. Not interpose, but switch. 1276.28. 127. All right, so you know that the T is going to be much more than 5 years because we have to triple our money. We haven't even doubled it yet, so it's going to be a lot of years. Let's see how many years it is. Divide both sides by 1,000. That gives you 3, the multiple. And then how many times do we have to hit it with 1.05 before we get a multiple of 3? Again, the variable's in the exponent, so don't take reciprocal powers. Take logarithms, take base 10 logs because they're easier. You're not going to be able to write 3 and 1.05 as powers of the same base. So we'll go with base 10 logs, and we can bring the t out front. That's the reason we use the logs, so we can get the variable sprung from its exponential dungeon, and then we are power, I guess, and then we could divide both sides by log of 1.05. And we successfully freed t. T is equal to log of 3 divided by the log of 1.05, 6. That's a 0. And plug that in the calculator, and we get 3, take the log, divided by 1.05, take the log, and we get 22.517 years, which seems like about right. 22.517 years. And a quick check on this is the rule of 72, the rule of 70, I guess, either one, depending on what you prefer. 5%, 5 goes into 70, about 14, it's 14 exactly, I think, right? Yeah, so the rule of thumb is to double your money in about 14 years. That's doubling. This is doubling time. just basically the rule of thumb. That's your double time estimate. Somebody says divide 70 by 5%, and you get roughly the amount of time to double. So if it takes 14 years to double, 22.57 to triple seems reasonable. It's not going to take another 14 to go up by, to gain by, go from doubling to tripling. All right. Radioactive sample weight 100 grams at 8 a.m. Newton weight 77. So we're looking at a table here of here's T, and here's the amount at time T. 8 a.m., which we'll call time 0, we had 100. And noon, which we'll call time 4, because it's 4 hours after 8 a.m. We had 77, and we're asked to find out how much is there at 6 p.m., which is 10 hours, 6 hours past noon, so 10 hours past 8. So that we're looking for this number here. So we'll start by putting in the information we know. It's sort of like finding a slope, although it's, in exponential case, it's like finding a multiple. So 77 is A of 4 is equal to the initial amount, 100, times the rate. We don't know what the rate is, 1 plus R, but we know it takes 4 years of hitting 100 with the 1 plus R stick to turn it into 77. Divide through by the 100, as we almost always do. Divide through by the initial amount to get the multiple. And then take the fourth root. So you get 0.77. Fourth root of that equals 1 plus R. And then don't solve for R. Please don't solve for R. Please don't solve for R. In these problems, you don't need R. You're just being asked to use 1 plus R to find the amount at other times. So plug this in for 1 plus R in the basic equation. So instead of the usual A of T equals A0 times 1 plus R to the T, we now know that 1 plus R is equal to 0.77 to the 1/4. That whole thing is being raised to the T power. So power to a power, we multiply them. So this becomes 0.77 to the T over 4. And we know the initial amount at time 0 was 100. So this equation allows us to find the amount of the radioactive sample at any time. So the exponent here is basically counting the number of 77% or 23% reduction period. 77% multiple is a 23% reduction. It happens every 4 hours, so T over 4 takes the time in hours and decides how many 0.77 intervals it is. Just like the half-life formula, which would be a half times T over H. But now instead of the time to half, we have the time to be reduced by 23%. And instead of halving, we're reducing by 23%, which is 0.77. All right, so get rid of all that. All right. So now we're looking for A of 10, right? So we just plug that in. A of 10 equals 100 times 0.77. 10/4, which is 10/4 is 2.5, so it's 5 halves, or 2.5. So we're hitting 100 with the 0.77 stick 2.5 times. So I'll change this to 5 halves. Let's turn it into 5 halves is 2.5. Let's turn it into a decimal, so we can easily plug it in the handy Windows 10 calculator. So there, and 100 times 0.77 raised to the 2.5. That's 52.027. Round to 3 decimal places. 52.027. This is 52.027. And you do another reasonableness check. So at noon we had 77. So 23% reduction again at 4 hours later, which would be 4 p.m. We would have 77% of 77%, which is around 23% reduction is going to be around 50-ish, more or less. So we had a little bit longer to go to get to 52. So that seems reasonable. It's certainly less than 77, which is what we'd expect. And it's less than 77 times 77 times 100. You can check that. 277 periods would just be 0.77 squared. So if you take 0.77 and you square it, that's a reduction of 41%, roughly. So 52.9, 59.2, a 59 multiple is a reduction of 41%. So we're not down to 52 yet. That's after two 77% periods, 23% reduction periods. All right, moving on to population of bacteria doubles every 4 hours. How much longer take to increase by 3 times? So you can do it with the doubling formula, or you can do it without the doubling formula. With the doubling formula, it's easier. The doubling formula looks, if you remember it, looks like this. T over the time to double. And we know that the doubling value, so we know that this guy right here, we're looking for how long it takes for A0 to go to 3 times, 3A0, right? We want to turn A0 into 3A0. We want to, A0 is the initial amount. The final amount is 3A0. We're trying to triple our money, or triple our bacteria in this case. So we divide through by A sub 0, we get 3 equals T2, sorry. 2 to the T over 4. And now we have to take base 10 logarithms of both sides because the variable is in the power, not in the base. So we don't use reciprocal powers. We don't use 4 over T. And we can't write 3 and 2 as powers of the same base. So we're forced to resolve to base 10 log of both sides. We bring the T over 4 down as a multiplier. That's why we went to logarithms. Last rule for logs. Let's just do that. We clear the fraction, multiply everything through by 4. And then we have number times T times number. To find out what T is, just divide by the number that's being multiplied by T here. And that gives me this. There's my answer. So that's a calculator ready expression. T, notice I did not compute any intermediate values and drag them along. I waited until the very end. Do all my calculating all at once. So that's 4 times the log of 3 divided by the log of 2, which is word of operations problem. 4 times log 3 divided by log 2. So log 4 times 3, take the log 2, 6.34, 6.339, round to 9 goes to 6.340. 0.34. Only times 4 hours, 3 times, that would seem like a reasonable number. It's certainly more than 4. For 11, effective yield is in order to get through the smoke screen of different compounding periods, banks were forced to tell you exactly what happens to $1 in 1 year. As you said all along, the signature of exponential growth, the equivalent of a slope, which defines a line. You just need a multiple in the time to reach that multiple. If you have a multiple in the time to reach that multiple, then you've completely defined the growth, regardless of how often you say you're compounding. It doesn't really matter how often you say you're compounding. What matters is what does a dollar turn into in 1 year? So this is $1 for 1 year. So using the compound formula, the value of at 1 year of $1 times 1 plus 4% given in 12 installments in a year, that would happen 12 times. And we should put a 1 up here, but it's only a year. That's the number of months in a year times the number of years gives you the number of compounding periods when you're compounding monthly. So that's just a calculator exercise. If you do this, you'll get 1.0407 roughly rounded to 4. So this is 4.07%. So when they say you get 4% compounded monthly, that actually means 4.07 in a year. $1 turns into $4.07 in 1 year. With continuous compounding here, do it up here, I have more room. Continuous compounding says the value of $1 in a year is $1 times e to the r times 1, right? Continuous compounding is a0 times e to the rt. Well, t in this case is 1 year, and a0 is $1. So this just simplifies to e to the r. E to the r tells you what $1 looks like in 1 year with the annual interest rate of r. It's going to be bigger than the interest rate. You're going to get more than 4% here, right? Because you're compounding continuously. In fact, you'd get even more than 4.07% because compounding continuously gives you more money than compounding annually. So what we have to do is this r is going to have to be smaller than 4% in order to ratchet down the continuous compounding to be equal to the compounding every month. So if we put 4% in for r here, this number at continuous compounding would be bigger than 4.07, and we're supposed to make it equivalent. So we're actually going to need an r value that's less than 4% for continuous compounding to be the same as monthly compounding. So we just set e to the r equal to the continuous, the monthly compounding to this. And this turns out to be really easy to solve because we have a base e expression here. So take the natural log of this mess on the right. The natural log of that guy is r, because e to that guy, the e to the r equals that guy. So there's an e here. E to the r equals this. That's what that expression says. So all you have to do is take the natural log of the expression we just had up before. So I think that expression is probably still up there on the calculator. There it is. No, I lost it. Okay, so did I ever even get it? I did. I never computed it. So let's compute it just to check that number I put there. So let's go back to part A, which is 1 plus 0.04 divided by 12. Yeah, let's put that in parentheses because I'm not sure how good your calculators will be with order of operations. So let's be careful here. 1 plus 0.04 divided by 12, close parentheses. And then we're raising that to the 12th power. So I got the other one there. All right, try again. 1 plus 0.04 raised to the 12th power is just what I said. It was 1.0407415. So roughly 4.07%. And so now we take the natural log of that number. That's what this says to do right here. It says take the natural log of the number we just computed. And so we take the natural log of that. And we get, oops. So that's what we're looking at. 1 plus 1 raised to 12. That, and I take the natural log of that number. And I get 0.0399. So 2 decimal places, that's 039. If I round it, I get 4. So I'm just going to leave it as 0.0399 just to show you that it's not 4. R is equal to 0.0. Room here. 2 little rooms right with the mouse. This is 0.0399. So it's awfully close to 4%. It's a little bit less than 4%. So what this means is if someone offers you 0.0399% compounded continuously, that's the same as 4% compounded monthly.